Good day, folks. Here's another question of the photoelectric effect. It's a past question paper. Let's cut the chase. The photoelectric effect has many practical appliances. A photocell, such as the one below used in burglar alarm system, is one such application. Guys, this is that white thing that looks like a camera that it's on the corner of the houses. So when it detects you, or when you interrupt, its light there, it will be off. Now it says an ultraviolet wavelength of 100 nanometers is illuminated in the photocell, which is this is the photocell. There is a light here with 100 nanometer, that's the wavelength there. So do you see this light? It goes straight to the cathode, and then the photoelectric effect occurs. There are electrons that are ejected there. So these electrons in the cathode, they go to the anode. Now it says when a person interrupts an ultraviolet beam, the sudden drop in the current activates a switch which sets off the alarm, right? Now 14.1, it says define the term threshold frequency. The threshold frequency, guys, is the minimum frequency needed or required to emit the electrons on the surface of the metal, right? Stick to the exam guideline. How will an increase in intensity of ultraviolet influence an ammeter reading? So this ammeter reading, if you change the intensity, which is the brightness of this UV light, how will it going to affect the ammeter reading? Surely the ammeter reading will increase there. So the answer in 14.2, the ammeter reading will increase. Increases. What is the reason? Right, increase in intensity of UV light. UV light increases the number of photons per second or per unit of time, right? And also increases, when you increase the intensity, increases the number of photoelectrons emitted per second or per unit time, right? That's one of the reasons for the increase in intensity. It increases the number of photons per unit time, and it increases the number of photoelectrons per unit time, right? 14.3, it says the work function of the metal used as a cathode in the photocell is, this is the work function. It says calculate the velocity, which is we want the Vmax, in which the electrons are emitted, right? So in 14.3, so we are looking for Vmax. We are given the work function. The work function is 8.7 times 10 to the power 19 joules. So which formula are we using? We use the formula energy is equal to work function plus EK max, right? So based on what we have, do we have an energy? No, but we have the Planck's constant, right? We don't have the energy, but we have we have the Planck's constant, and we don't have the frequency. From this formula that says HF, we will use the one that says hc divided by lambda. It's going to be hc divided by lambda, since we don't have frequency, but we have the speed of light, and we are given the wavelength. The wavelength was 100 nanometer, which is it's 100 times 10 to the power negative 9 meters. We were given the frequency, the wavelength of the UV light there. So the work function we're given, no need to expand, but the kinetic energy we have to expand because we want the velocity is going to be half mv max square. We are looking for v there. We'll substitute. We will substitute, and we're going to have 6.63 times 10 to the power negative 34, which is that's the Planck's constant. We multiply by the speed of light, and then we divide by 100 times 10 to the power negative 9, which is the wavelength, and the work function is 8.7 times 10 to the power negative 19 plus, and then we go to m. The m, guys, is the constant. It's 9.11 times 10 to the power negative 31, and then we want the velocity. Remember, this velocity is square, right? So this answer, you take it to this side, and then all this you divide by 9.11 times 10 to the power 34, and then you put the square root. So your answer there, it will be your Vmax there, it will be 1.57 times 10 to the power 6 meter per second. That will be the velocity of the photoelectrons emitted there. I hope that makes sense, guys. Cheers. Bye.